Hello, everybody. My name is Nicola Timeus. I work as a software engineer for Eurotech, and I'm also an Eclipse Kura committer. With this talk, we want to provide you an overview of the Eclipse Kura Wires data flow programming environment. I want to show you the concepts behind it and how it works, then show you the current state of the ecosystem, showing you what are the available components that we have and what you can actually do with this framework, and also show you how it is being used in the field. So first of all, to set some context, Eclipse Kura is a framework to build IoT, is an IoT edge framework that runs on IoT gateways and allows you to manage the gateway in all of its aspects, from network management to security, data acquisition, publishing to the cloud platforms. And on top of Kura, we built ESF, which is our proprietary IoT edge framework based on it. Kura, or ESF, runs on an IoT gateway, as you can see there, that usually is connected to some sensors, actuators, or other devices like PLCs that you have on the field. You want to gather data from them, do maybe some processing, and then send it to the remote endpoint. This is one of the typical use cases that we address. So let's talk about Kura Wires and how it fits into this. So as said, Kura Wire embraces the data flow programming model. With this paradigm, you represent a program, an application in terms of a graph. A graph where the nodes can be processing, can be computations, processing, can be data sources or data sinks. And those nodes are connected by edges that represents the data path that flows between them. We found that this fits particularly well to an IoT scenario when you have data acquisition, processing, and publishing. And as you can see here, it is really easy to see the data that is moving between these components. It's basically a graph, even with a single branch. So as said, Kura Wires allow you to use this programming environment, this programming model within the Eclipse Kura framework. The graph nodes in this case are called wire components and the edges wires. Let's see what are the goals of this framework and the benefits of it. The first and maybe the most important goal is simplicity. We want to enable also people that doesn't have strong programming skills to build an IoT application and we do this by raising the level of abstraction. So we don't want you to think in terms to deal with the field protocols involved directly. We want you to write low code or no code if possible. The data model that is exchanged between these components is also very simple and easy to understand. And of course, we have a user interface, right, within Kura Web UI that allows you to manage everything and to draw your applications. As said, Kura Wires is not standalone, but it's well integrated with the rest of the Eclipse Kura functionalities. So Kura is based on OSGI, and the wire components are just like the other services. There is nothing special with them. And we already provide a lot of components that expose the main functionalities of our framework, like cloud interaction, data acquisition. We have also added Edge AI recently. And another great benefit that you get from using Kura is portability across different gateway architectures. So Kura is all about abstracting away your application from the underneath operating system and hardware. So once you develop your solution on a single gateway, it is really easy if you want to switch. You just have to export it. We have a configuration format that can be used to represent graphs and deploy on other gateways, also of very different architectures. Another goal is extensibility. Of course, everything is based on OSGI service interfaces. Everything is open, and you can create your own wire components simply by implementing those service interfaces in a well-defined way. Of course, if you are dealing with IoT, you want absolutely to be able to manage your devices and the life cycle of them, and also the life cycle of your applications remotely. So you can manage this in different ways. Through the local console, of course, but then once you develop your solution, you can export it in a configuration format and deploy them from the cloud, for example, with Eclipse Kura, to a single device or also to a fleet of devices. And we provide also local REST APIs to do this if you have an external application that wants to locally configure a wire graph. So all this contributes to, first of all, reduce the time to market because the development workflow is really simplified. You have a high level of abstraction. We highly encourage component reuse with this. So you have some simple building blocks that you combine together to build your application. And then we have a well-defined life cycle and portability benefits. So let's look in detail how Kura Wires looks like. As said, the graph nodes are called wire component. Here you can see the rendering from our component from the web UI. They can have a configurable number of input and output ports. And the edges that connect them are called wire. They connect an output port of an emitter component to the input port of a receiver. The communication on the wires is message-oriented, so you have messages flowing there that are called wire envelopes. So let's see what's inside these envelopes. The data inside is organized in a map, in a set of key value pairs, where the key is a string and the value belongs to a small set of data types. You have numbers, booleans, strings, and byte arrays. So we defined this data model to be something that is simple and easy to understand, but we found out that is enough in most of the cases. So, as said, you can develop your application visually. So let's see how this looks like. You can simply drag and drop the components on the canvas. You assign them a name, and you connect them together. Each component also has a configuration section that you can access right from there, and you can configure the parameters that define the behavior of the single components. Once you're done, you can save the configuration and maybe also export it to other gateways if you want. So let's see what component types do we have and common patterns that you can implement. One component that is used a lot is the timer, and its purpose is to trigger the execution of the downstream branch. It can configure to emit envelopes at a specific time instance. You can configure it in simple mode when you will have a constant delay between two graph executions, or also with a cron expression to have everything happen at a specific time instant. Another component is the logger that can be used for debugging purpose to dump the content of the envelopes on Kura log, or you can use it also to develop a black box recording, a data logging application to the local file system. Of course, another common pattern is publish-subscribe. So we have some components that interact with the Kura cloud platform abstractions that allow you to send and receive data to different cloud platforms with a single interface. So we have pluggable cloud platform implementations that you can use with the same interface, and it's really easy to switch between them. So there is no lock-in. Once you have your application that publishes on a platform, it is simple to switch to another with this model. You might want to store data on a database, and we have components to do this. The DB store is able to store the wire envelopes on a local database instance. In Kura, currently, we support the H2 database. And you have another component that is able to retrieve the data on it and make it available back on the wires. Since everything is message-oriented, you can implement some simple messaging routing patterns. For example, we have the condition component that is able to evaluate a simple Boolean expression on the content of an envelope. And if it evaluates to true, it will trigger one branch and the other one if not. So this, for example, allows you to detect some conditions on the data, for example, to implement a simple alert. And sometimes you also want to merge together several different wire branches. For example, you have components that acquire data from different field devices, and you want to use everything in a single envelope. You can do this with the join component. Of course, you also want to do some processing locally on the gateway before sending the data to the cloud platform, maybe to spare bandwidth. We have a couple of components with this. We have one that allows you to filter the data based on simple regular expressions. We have the AI component that allows you to perform machine learning computation directly in the graph, and a JavaScript filter that allows you to create small scripts that manipulate the envelope content. So the AI component has been added recently in the latest Kura release, and it allows you to integrate with a so-called inference engine service that is a library or a server that performs edge AI. And the component allows you to send the data to it that will do some inference, some machine learning, get the result back, and have it available on the wires. Then we have the JavaScript filter that, as said, allows you to perform some manipulation on the envelope properties. Here we have code back in the picture, but this is really simple code at a high level of abstraction. You don't need to deal with the low-level details of the field protocol. You just have to transform some maps, and this is really simple at the end. And perhaps the most important use case is also being able to interact with external stuff like field devices or sensors. And we have created a specific model for this called driver and asset. So a driver is a component that encapsulates the implementation of a field protocol and allows you to think in terms of data points that are called channels. A channel can be, for example, a Modbus register, an OPC-UI variable, but also a digital input, a digital output. And you can perform the read, write, or listen operations on that in a uniform way. An asset is another abstraction that that groups a set of data points and persists them. Usually an asset represents an actual remote device accessible to the driver. But let's see how this is configured in practice to get a better understanding. For example, suppose that I want to use OPC-UI. I will need to create an instance of the OPC-UI driver. Once you do that, sorry. Once you do that, you will have your instance available here. You can review its configuration options that will contain, for example, the endpoint of a remote PLC and a server name. So here you have protocol-specific details that you have to configure. Once you perform the global configuration, you can create an asset that will store your data point configurations. For example, here we have created a PLC1 asset, and we define some data points. For example, we want to read an analog input from it, and we want also to update the value of a switch. So we will configure the first channel in read mode and the second in write mode and select the proper data types for it. Now you will switch to the OPC-UI specific configuration part, telling the asset where it should find these data points, providing the node ID and node namespace index, which are how variables are addressed in OPC-UI. Once you're done this, you can forget about the fact that you're using OPC-UI and that you are referencing those variables. You just need to remember the channel names that will be used later on to reference to those components. The web UI will also allow you to test the communication once you set up everything. So once you define an asset configuration, you can use it on the wires. This is a simple graph that performs a read. You have a timer that periodically triggers an asset instance that will read the channel values and emit them on the wire in that simple format. You have the channel name as key, and the value is as the channel value, pretty simply. If you use listen mode, the driver is also able to send data point notification change events spontaneously. So you don't need a timer here. The driver will notify when something changes, and you will have the result on the wire with the same format as before. If you want to write, you just have to send a property where the name matches the name of one of the channels in the asset, and then send the value. For example, this will turn on the configured switch. So let's have a look at the Eclipse Kura Wire ecosystem and what you can do with it. Most of Eclipse Kura components that can be drivers or also wire components are available on the Eclipse Marketplace. And you can drag and drop from there right to your web UI. For example, you find an interesting component like the AI one, and you drop it on the web UI, and then it is installed. After a while, yeah. Now, you can go to the Wire Composer section, and for example, you have the new component available right here. And the marketplace is an open specification. Anybody can create custom components, deploy them there, and make them available. Also, there is the possibility to implement custom marketplaces to pull the components from. The number of components increased over time. We started with tens of components in 2017, and now we have more than hundreds of them. And most of them are field protocol implementations and wire components. After you install Kura out of the box, you will get these components available: timer, logger, the cloud publishing and subscribing part, the asset. These components are open source and maintained by the Eclipse Kura team. Some other components, open source and developed by us, are available on Eclipse Marketplace. For example, the eyewear component, the script filter, and some driver implementation. One that allows you to interact with GPIOs, Siemens S7 COM driver or PCUA, drivers for some development boards, and also Bluetooth. As Eurotech, we also maintain a lot of field protocol connector adapters that implements field protocols in different verticals, and they can all be used with the same interface. So once you learn the driver and asset model, how to configure it and how to use it, it will be pretty easy to use different devices that talk different protocols. Same thing applies to cloud connectors. We have an implementation of different connectors. Some of them are open source, like the ones that allow you to interact with Eclipse Kura, with Eclipse Kapua, our cloud platform, and we have also commercial components for the most popular cloud providers that you can, and it's really easy to switch between them. So let's see now how this is used on the field. One use case that I want to mention is DB Cargo, which is a leading company in European freight rail transportation business that wanted to get a real-time insight of the status of their fleet. And we've been able to address these requirements with Eclipse Kura Wires. And we have an application deployed on hundreds of trains. This is interesting also because Deutsche Bahn is also an Eclipse Foundation member, and it was really important for them to have a open solution, both open source and also configurable and extensible. So how does a wire graph look like in the field? Well, it depends. If you have a simple use case like this, acquire data and publish, you are basically done with 3 components. You just have to configure your asset, select the data points, and publish. So this simple common scenario is simple to implement. But this is not obvious, because if you have to do this from scratch, it takes a lot of time. You will need to find a field protocol stack implementation, learn how it works, integrate it, find the cloud platform stack, and test the whole thing. So it's complicated. It requires time and some effort. With this, you can have this ready in minutes, basically. Of course, you can address also more complex scenarios, in this case by composing simple and reusable components to create your application. So the complexity is addressed using code reuse and component reuse. Usually you have a small set of component types that are used along with these graphs. Some of our customers are fine with a low-code approach, so they are fine with using the JavaScript filter, and they can write some code or implement also custom components in Java. Some other customers want a completely no-code approach. In this case, what we usually do is implement some specific components that address their need. For example, if they need to have additional logic that is not available, not supported by the existing ones. And we try to give them something that is easy to configure, easy to reuse. So at the end, rather than a closed solution that does a single thing, they get a tool set, a set of tools that they can combine to address also different needs. Another application that I want to mention is protocol conversion. So, for example, suppose that you have two PLC, two devices that talk different protocols and incompatible ones, and you want to have them talking together. You can use also a Kura wire to do this. If you can model the whole thing as a data point transfer between two drivers. And initially, this application was not foreseen, but it is something that came out for free. Basically, you can do this. You have an asset that reads from one protocol and writes to the other, and you can have also the other way around. So briefly, in the future, as future extensions, we will try to add discovery support in drivers, because currently you have to manually configure the channel of your assets. Of course, you don't have to do this every time because you can import and export the configurations, but some protocols like OPC UA allows you to browse the data points on the server dynamically, find out what they are, and having this available would simplify the initial configuration phase. Another common use case that we will address is creating an asset template library. So, for example, you have a specific PLC with a well-defined set of data points. It would be nice to have an already filled asset configuration for it that you can get and install from there. And last but not least, we want to add support for more database implementations besides H2. And that's it. I would like to thank you for your attention. And if you have questions, feel free to ask.